with a short attention span or those who already experienced in memory management or marathoning this event for more than 12 hours in a row. Here is a short key points. Next slide is also will be citing a recent work which have a lot of novelty, and the rest will be probably mostly a recap of known papers. So this is how we structure our today's talk. Takeaways. First of all, almost all samples are naturally good for memory. It is usually the question of which samples are less representative or less useful for mitigation of catastrophic forgetting. And we want to keep as much as possible. But with more memory, usually we can see less of a performance gap between complicated and simplest methods like experience replay. One of paper which can demonstrate it is Dark Experience for General Continual Learning, great paper with a lot of replay-based methods benchmarked. Next thing is awesome, great, prominent, and very complicated and computationally expensive methods can benefit from combining with some cheap strategies for faster selection. And my argument why it can work, it's because not every batch, not every model update would have some crucial samples to preserve in the memory or some samples which dramatically decrease performance and should be removed from the memory. So we shouldn't expect that there is a subset of samples which would be optimal and absolutely perfect as a replay buffer, as a memory buffer. No, I think most probable that will be a wide range of samples that we can store in a memory buffer without any changes in a model's performance. So probably we can skip some steps when we select samples to the memory buffer and make things faster and cheaper. Last one is removing samples from the memory buffer. On my opinion, according to methods which I reviewed for today's talk and for literature review for my other works, is quite under-investigated. And this is not good because probably sometimes it is more important not to remove some great sample from the memory buffer than apply one strategy to select the samples to the memory buffer again and again with huge computational overhead. But this is like preliminary results of my current research. It is not published yet, and I can't have some hard proofs on this take. But let's proceed. First of all, let's discuss what is the difference between standard or offline continual learning and online continual learning. To demonstrate it, I selected actually a very fresh figure from a preprint that I read just today. It's a nice paper with a simple idea. What if we take the usual Cypher 100 dataset, for example, and instead of having some number of tasks, instead of splitting it on tasks by, for example, some number of classes in each task, we have only one task with all classes present, and we train the model in online fashion, like a regular one. And the outcomes of this paper, that is why I shuffled a few slides and modified my presentation for today's talk just in the latest moment. It is awesome to see that, first of all, the difference between online and offline learning greatly depends or greatly defined by surprise, the difference between online and offline learning, not by the distribution shift, not by task shift as it occurs during online learning, for example. I'm not sure how they isolated this specific reason in performance drop from other ones, so don't ask me. But evidently, from results table, at least half of the performance drop, which we can observe when we train a model in offline fashion and online fashion. I'm not sure if I should clarify what is online and offline, but okay, let's do that fast. It's basically about the size of chunk of the data that's currently given to us. And if this chunk includes all data associated with some task, then it is offline learning. If we have chunks that only partially cover the current task, that we treat as online learning because we can see this batch of samples only once, unless we put some of the samples to the memory buffer and then revisit it. But yeah, generally, if we saw some sample once and move to the next chunk, previous samples are lost to us, and that's why this setting is much more complicated. And comparing to the standard and online continual learning chunking is a situation when we have only one task and we present it with a sequence of batches with all or almost all sample classes presented in this chunk, but still we can't revisit previously seen data, and we have to rely on continual learning methods, specifically on memory-based methods, to revisit some samples from previous chunks, and that's how mitigate catastrophic forgetting. And yeah, outcome of this paper is two observations. First one is that this chunking situation, basically online continual learning or online learning without splitting on tasks, is responsible for half of the drop of performance between online and offline learning. This is a huge problem. This is a huge sub-problem of online continual learning problem. And since it is only now was exposed directly in this paper, I assume that all methods of continual learning does not directly address this chunking situation, and probably they can benefit from some improvement in this direction. Or they can benefit from combining current strategy with selecting samples using some other property of the sample. I will explain what is property of the sample a bit later. And the second observation is that all explored continual learning methods, which is experience replay, DAR++, AGM, and gradient sample selection, they all failed on this chunking problem. So in chunking setting, when they have only one task, online learning, they behave uh, as good or identical to regular SGD training. That is crazy. That means that a whole direction in continual learning wasn't covered. But yeah, let's go on to the properties of memory buffer. But this figure is actually from a paper on active learning, and they have a binary classification problem where we have white circles and gray squares representing two classes. We have black line, which is decision boundary, and we have red dots, which are selected batch or selected subset based on corresponding property of this subset, which is informativeness, representativeness, and diversity. As we can see, informativeness is picking samples which lie on or close to the decision boundary. Representativeness is just sampling from the most dense part of distribution. And diversity is uniformly sampling across the whole, for example, feature space or gradient space or whatever we use to distinguish between samples in our replay-based method or any continual learning method. And first of all, this paper is this method or this classification is applicable also to continual learning, despite being originally for active learning, because we also should select some samples to the memory. And yeah, informativeness. Informativeness. Sorry, can you see my presentation actually?
Yes.
Okay, great. Informativeness is not quite applicable to continual learning, or rather, we have different definition of informativeness in continual learning, since new decision boundaries may appear when we have new classes, new income classes, and because of that proximity to all decision boundaries may not play out. So for the new decision boundary, we will have to select samples which lie near this boundary, and we don't have this opportunity because we can't revisit old data from old chunks, and in current memory buffer we store only samples that are close to other decision boundaries. Okay, you got the idea. Key point: we should pick samples that are probably have some combination of these three key properties and store it to our memory. How it works? Simplest example, memory replay, it could be online memory replay, is when we have data stream and we pick some samples from this data stream and we have memory. We have special procedure, batch sampling, to pick samples from the memory to put it to replay batch, and then we replay online batch and replay batch together, put it to the memory, and that is how we try to imitate whole distribution of currently visited classes or tasks. But then we often use some features or gradients or losses, uncertainty, whatever, extracted from the model for a procedure called memory updating, which is self-explanatory. We use it to update sample storage in the memory. This is actually a figure from my old paper, which is about combining reservoir sampling from a quite expensive strategy of selection samples to the memory buffer by extracting embeddings from the layer of the main classifier. So this layer is hyperparameter, but usually the last one prior to classification head is good enough. And we should do this embedding extraction as often as possible. So fresh embeddings are better, but it is not obligatory to do it all the time. We can have some delays, but sacrifice with performance. And then we compute pairwise cosine similarity between these embeddings. And this table, huge table of pairwise cosine similarity allow us to identify pairs of samples with closest distance between them, and then reject one of the samples. It is quite expensive. We found a nice implementation which makes it relatively fast, but still it is obviously computationally expensive. So riding or piggybacking on reservoir sampling allow us to skip a lot of such steps and makes it faster and obtain results faster. So this combination is quite effective, I think. And I see that I dramatically run out of time. Do I have?
Yes, unfortunately, yes. It's very
Okay.
interesting. If we could wrap up, that would be fantastic.
Yeah, sorry, I haven't been talkative since. Yeah, it was a great event, and I had a lot of fun. And yeah, I can stop here. You can contact me at any time.
So we do have a few questions, and we have a little bit of time for
Okay,
Q&As.
let's do that.
I should go ahead. Okay, so the first one, in online learning, each batch entering the model for training is considered as an experience. Please clarify.
Okay. In online learning, each batch entering is a batch of experiences. Naturally, we can treat it as one batch in some gradient-based learnings when influence of each separate sample is not that important. But key idea of online learning is one sample seems only once unless it is present in replay buffer. Offline learning is when we have access to the whole task and we can feed the model with many batches sampled from this task and do it, for example, in a few epochs. So train model better, or having access to the whole task, we can select better subset of tasks of samples to be preserved in a memory buffer. So this situation is simpler than online learning.
Wonderful. Then we have a second question by Marty. Can you expand on the difference between information and diversity in that one slide, which includes the ability for representation?
Yes, of course.
I think this is correct. Is information more oriented towards minimizing error in a statistical sense, and diversity more oriented towards a tessellation of the future space?
Well, the thing is, I have a great example of strategies that select samples to the memory buffer and from the memory buffer. To the memory buffer, it's consistency-aware sampling, and from the memory buffer is MIR. It is pretty popular approach. I can post links to the chat a bit later. The idea is these both strategies are score-based. So we estimate informativeness of each sample stored in the memory buffer or in the current batch that we consider to store in a memory buffer. As each sample have a score. In MIR, the score is based on, for example, difference between losses computed for sample before and after the memory update. I'm not sure if I explained clearly. So we have a memory buffer, we have 100 samples stored there, and we have classification model. When we compute losses for all 100 samples stored in a memory buffer. Then we update model on an online batch, on a fresh data from the fresh task. Then we again compute losses for all samples in a memory buffer. And then we search for the highest difference between losses prior and post this update. And the more losses changed due to this update, we presume that current update interfere the most with the samples. And we want to select the most interfered samples to be replayed again to the model, so the model can rehearse this information and mitigate the influence of this interference. But the problem is, when we compute difference between losses for each isolated sample, we receive a score for this sample. And then this score we treat as informativeness. No, not abuse. The score we treat as informativeness. But problem is, the similar samples most likely would have similar scores. Like if the model forgets an image of a cat, most likely image of a same cat would have similar score. And if we pick most informative samples based on this score metric and only on this score metric, we risk to obtain very similar samples in a memory buffer, in the replay batch sampled from this memory buffer. So we have to increase the diversity of this subset of samples. And we selected not only the highest metric, not only the highest score, but for example, random samples from top 10% of this score. This is how consistency-aware sampling working. In case of MIR...
Sorry to interrupt.
Sure.
That this is very informative. I think it's a very clear explanation. If you could wrap up so that we have time for the next presentation and a short Q&A as well.
Yes, sorry. Basically, my answer is these three properties are differ between each other. They can be combined by one strategy, but it is not guaranteed that most informative samples are most diverse or any diverse. Is this an answer?
Definitely. That was
Great.
The explanation itself was super clear. Marty also asks how this relates to, for instance, AWS. If you could reply that in the chat, that would probably be that would be wonderful. And of course, you suggested you would like to share some links. Please do that in the chat, because we do want to continue the discussion, but right now we do need to move on to the last oral of this session.
Sure. Thank you very much.
Thank you. That was a great presentation.